Okay, chapter 12, classroom discussion. Trying to figure out sound waves. Okay, the very first problem is a very interesting one in terms of applications. You have two stereo amplifiers, and I'm pretty sure you've noticed how uh, manufacturers always try to sell you the most amount of watts. There's going to be like a bright sticker and says 1,000 watts, 2,000 watts. This one has more power, it's more powerful, and stuff like that. Let's see what is the difference in terms of power. You can see the power is 75 watts per channel, and the other one is 120 watts per channel. Let's see what is the real difference here in terms of decibels, in terms of loudness, in terms of this convenience scale that we discussed as alternative to System International, because System International would be watts per meter squared. Let's see how it's going to go in decibels. So which one is more powerful? The formula for conversion from intensity to loudness is shown here. And basically, we are comparing the two intensities that will be created for from a sound system with 75 watts versus the intensity that will be produced by 120 watts amplifier. So it's 10 times the natural log. It's not natural, it's just log base 10, I believe. And you have 120 versus 75 for the intensity. What is intensity? Remember, intensity is watts per meter squared. It's the power output per surface area. Power output, that's right there. That's what you have. And the surface area would be the surface of a sphere. Consider the sound system being the source, and sound waves will go uniformly in every direction. So you can think about an imaginary sphere that surrounds the source, and those sound waves will hit that sphere, and the surface of a sphere is 4 pi r squared. Remember, it's 2 pi r for the circumference. Pi r squared is the area of a circle, but this one is not a circle. It's not a two-dimensional geometry. It's the surface of a sphere. So 4 pi r squared. And it's the same sphere for both amplifiers. You have two amplifiers to compare, so you put them in the same spot, and it's going to be the same imaginary sphere with a surface of 4 pi r squared, r being the distance between the source and the sphere. And you can see that it doesn't matter how far away you put those speakers away from the detector, you will cancel the 4 pi r squares anyways. So instead of comparing the intensities, we are essentially comparing the power output. And it seems like it's, quite a difference, because it's, 120 over 75, that's like 1.5, like 50% more. But let's not forget that there is a log function, and log, usually makes everything very small. Like a log of a very big number will still be a very small number. So natural log or log base 10, doesn't matter. You will get a very small number, multiply it by 10, and you will still get only 2 decibels. Remember the 2 decibels? It's not really even a jump in the grade of, like, say, from talk to a loud conversation. And like, honestly, you will never even recognize the difference. The 2 decibels, it's really nothing. Quiet radio gives 40 decibels for you to think of. So if the quiet radio gives you 38 decibels versus 40 decibels, you will never ever hear any differences. So do not overpay for the power. Power means nothing. Yeah, there is a little bit of a difference. I can't say there is zero difference, but it's such a small difference that there is no point of paying double the price for double the watts, for double the power. It's only the loudness, the parameter from the intensity divided by the area that really matters. So do not pay for double power. Pay for the decibels, not the watts. Okay, next practice with that decibels formula is the power output of a sound from a person speaking. Like right now, I'm a normal person speaking, and yeah, we can use a table for that. I remember it was 60 decibels. And the sound spreads uniformly, yeah, over a sphere. That's what we consider the 4 pi r squared, the area, the surface of a sphere. And the second question is, how many people would it take to produce a total sound output of 60 watts of ordinary conversation? See how you have to add intensities, not decibels, because we're talking watts. Let's see what we have here. First of all, intensity of a normal conversation at a distance of about half of a meter, 50 centimeters, is approximately this much. We got this number from the table, which corresponds to, I don't remember, 50 or 60 decibels. So either way, this is your System International for the intensity, and intensity is power per surface area. So what kind of a surface? It says it's a sphere, so the surface of a sphere is 4 pi r squared. So if I want to solve for the power, which is the question, you have to multiply the intensity by the surface area. That's exactly what we're doing here. Intensity comes from the table. Here it is. And 4 pi r squared, be careful, do not do centimeters, convert to meters, which is half of a meter. And then you have to square it. Do the math, you're going to get 9.4 times 10 to the negative 6th of a watt. And you might say, hey, it's a very small number. But I want to remind you that our threshold of hearing is 10 to the negative 12th. So this is already quite a power output compared to 10 to the negative 12th. This is like a million times more. So not a small number. And to produce a total sound output of 60 watts, well, if one person produces this much, then for the 60 watts, you have to use the conversion factor that we just figured out. One person is this much, one person is this much. And we want 60 watts total, so watts cancel, and you're left with 6 million people. So 60 watts, which is funny how you remember the old school light bulbs, the incandescent light bulbs that your mom and dad used to use for your household. They had like 25, 40, or maybe 60 watts, and that wouldn't be the brightest ones. It would be just average light bulbs. So in order to produce the same wattage, the same power in terms of sound, that's going to take 6 million people. So light versus sound, you can see the difference. For sound, you need many more people, and that will be compared only to one light bulb. So once again, you have to distinguish between the power and the loudness, which is decibels, and the intensity, which is power per unit area. So make sure you answer the proper question. Is it the power output? Is it the intensity? Or is it loudness? Okay, and one last problem, but a long one for the Doppler effect. You really want to pay attention to this one. Focus, try to understand what's going on, and ask questions. We got a car, police car, and the original frequency is 1580. That's what the police car produces. That's like an average real world number. And it's traveling at 120 kilometers per hour. First of all, you say, oh my God, that's kilometers per hour. Don't you ever do kilometers per hour? Convert to meters per second. And part A is, what is the frequency that is detected by an observer standing next to a road? So standing means what? The detector is not moving anywhere. And the car approaches and then goes away. So honestly, part A actually has already two problems. The first one is when it approaches. Remember the wow, 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 higher pitch versus wow, 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 the low pitch when it goes away. And then there is a car traveling in the opposite direction, and then the car traveling in the same direction. Those are different stories. Let's focus on no motion for the observer. So just standing still, and the police car is going towards the observer and then away from the observer. Let's see what's going on. Yeah, first of all the kilometers per hour that you see, the 120 and then 90 and 80, we have to convert to meters per second, right? So kilometers cancel out, and 1 kilometer is 1,000 meters because it's kilo. Kilo means 1,000. And 1 hour, hours cancel. You're left with seconds. 1 hour is 3,600 seconds because it's 60 minutes, and each minute is 60 seconds. So we convert our kilometers per hour into meters per second. And it's time to use our magic formula. Once again, the f prime is what we're looking for, is what is registered by the observer. F is the original signal emitted by the source. V is the speed of sound, or it can be the speed of light if you're doing electromagnetic radiation. V sub D is the speed of the detector, and V sub S is the speed of the source. And you have plus, minus, minus, plus, towards, away, towards, away. So if you want towards for the detector, you go plus. If you want away for the detector, you go minus. If you want towards for the source, you'd go with minus, and away for the source, you go with a plus. So first part, detector is standing still. Remember, it was a person standing next to the road. So your detector is not moving anywhere. Your detector is just standing still. And the police car is coming towards the detector. So the source that creates the sound is moving towards the detector. The original signal, once again, was 1580. 1580 is what you would detect if there would be no motion at all. No Doppler effect, no motion, you would detect 1580 hertz. So you start with 1580, and then it's V, which is the speed of sound. This time we're doing sound, so just 340. And your detector is just 0, so it doesn't matter plus or minus, it's just 0. So just 0. You can ignore this part at all. And for the source, what do we see? The source is going towards. And for the towards, you have what? Towards, away, towards, away. So you go with a negative sign because this is the top option for the denominator in this formula. So minus And once again, make sure it's meters per second, not kilometers per hour. And you do the math, and you will end up with indeed what? The higher pitch, higher frequency. You measure 1580 with no Doppler effect, with no motion. But if a police car is coming towards you, you hear that wow, 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 wow. That's your higher pitch, higher frequency. Makes sense, right? Now, the second part of the same setup is when the police car is going away from you and you're still sitting still, you're still standing on the road, no motion. So detector is still 0. It doesn't matter plus or minus, it's just 0. And you start with 1580, and the speed of sound is 340. I keep on saying 340, not 343, because honestly, there's no difference. You can say 343 if you want. Still the same thing. And now it's the source that is going away, right? It was source that was going towards. Now the source is moving away. And it's the same formula, but now the source going away, towards away, towards away. So away is the plus option in this formula. So you go with the plus, not the minus. You do the math. And boom, you have what? You have a frequency that is less than the original. Original is 1580. And now you are at 1440. This is your wow, wow, wow instead of wow, 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 wow. So makes sense, right? That's exactly what you will hear next time you're on a sidewalk and you hear a police car or a fire truck coming towards you versus away from you. Check your senses, check your feelings. You will hear something different. Part B. Part B is a different story. Now there is a car traveling in the opposite direction. Okay? There is a police car going in a certain direction. And then there is a car traveling in the opposite direction to the direction of a police car. And once again, you have two options before the police car approaching the car, and then police car uh, moving away from the detector. So two cases for part B. And this is the source. This is the cop going one way. And the car, being the detector, is moving in the opposite direction. That's what's given. So here is our famous formula. The original signal is still what? 1580. V is still 340 meters per second. But now the detector is moving. Which way does the detector move? Which way is it moving? It's moving towards the source, right? Detector is going towards the source. If it's towards, remember how it's towards away, towards away. So for the towards option, you have to go with the plus. The top option is the towards option, so plus VD. And that's exactly what you have here. Plus the speed of the detector. The detector is going at what? 90, and we converted 90 as 25 meters per second. So plus 25 meters per second. Now for the source, what do we see for the source? The source is also moving towards the detector, right? You have the cop, and cop is moving towards the car. For the source, it's towards away, towards away. For towards, it's the negative option that you have to go. The top option is towards, the bottom is away. So if the source is going towards the detector, then it's a minus for the denominator, which is exactly what you see here. Do the math, and you get 1880 hertz. This is clearly, once again, more than the original. So every time you go in a certain direction and police car is towards you, you hear that loud "Meow, meow, meow," and you really want to just stop and move to the side and give way to cops doing their business, chasing someone. This is your, safety. Like your your senses will alert you right away. You just, give way and move away. So higher pitch makes sense. And then the police car is going away from the detector, and the detector is going away from the police car. After the police car passes you by, you will detect something different. Both the detector and the source go away from each other. So you have to go with away, away. Let's go to the formula. It's towards away for the top. And so away means the negative for the top. And it's towards away from the bottom. So if it's away, you have to go with the plus at the bottom. So minus on the top and plus at the denominator because it's towards away, towards away. So you go with away, away. So it's minus for the numerator, plus for the denominator. Minus for the numerator, plus for the denominator. You do the math, and boom, you have the frequency, which is less than the original. This is your wow, wow, wow. Makes sense. Moving on to the last option, option C. Option C says police car passes a car traveling in the same direction. And yeah, this is clearly a violation of traffic rules because if you see a police car behind you with sirens, you just, pull over and you stop. You don't travel at 80 kilometers per hour together with a police car. But let's say it's the freeway and, you just keep on going with that ratio. The point is, it's uh, the last option when both the source and the detector, they move in the same direction. So police car catching up with the regular car, what do you have? You have the source going towards the detector, but detector is going what? Away from the source. So police car coming from behind, but the direction of motion is the same. So two options: before it catches the detector, and then it passes the detector and moves further for their business. You have the first part when source is moving towards the detector and detector is moving away from the source. So detector is on top, it's towards away, so away for the detector away. Remember, it's towards away, towards away. So for away, you have to do the negative sign. And source is catching up. So source is towards the detector, towards away, towards away. So towards is the negative option for the source. So you have both negative signs, negative for the detector and negative for the source. And that's exactly what you see. Negative for the detector because it's going away, and negative for the source because it's going towards the detector. Do the math, you still have more. Well, something's coming towards you, you will hear higher pitch. Makes sense. Higher than the original. The original was 1580, now it's 1640 hertz. And finally, the police car has passed you by, and you can still hear the siren, but it's going away from you. So source is going away from the detector, but the detector is now going towards the source. So source is going away, and detector is behind, but going in the same direction. So towards the source. So source, so the top is the detector, and detector is going what? towards. Towards, away. So for towards, you go with the top option, it's the plus. And the source is going away from you, towards, away, towards, away. So for the away, you go with the bottom option, which is a plus. So for the denominator, you have also the plus. You got plus, 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 plus. And you do the math, and you have little less than the original because the police car is moving away from you. So you register still something close, but still less than the original. You will hear the wow, 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 not the higher pitch. So those are all the possible scenarios. You can see plus, plus, minus, 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 plus, plus, minus, and then zeros. All the possible scenarios are here for the Doppler effect. This problem really takes care of all the possibilities. Please study it. You will see something like that on the test. And in real life, you will definitely use this to do some calculations and figuring out how fast something's going towards you or away from you, or the geology or the medical imaging, or also many applications you can't even imagine. So classroom discussion is over. Moving on to our next activity. Stop recording.